So you finished year 11 and you're moving on to A-level physics, and you want to make sure you've got all the core data, information and knowledge. And waves was an area we didn't tackle in this very challenging year. The purpose of these three videos on waves and then Mr. O'Neill's ones on electromagnets are to bring you up to speed on the GCSE knowledge that you should have had moving on to A-level. So I'm going to go through it. It's really up to you what you write down, what you make notes of, which bits you want to take a screenshot of or anything, and then use that as you will. There's some questions that I want you to try out as we go along, but I'll try and explain it and go through it. And then you've also got my GCSE science, and there's a wealth of other information from the colleges if you go to their websites about starting the courses and the pre-learning. So what's a wave? Well, a wave is a way of transmitting energy. And if you imagine that this is the sea, have a look at it. It's pretty obvious that the wave is moving from the left to the right. But is it? Look at the blue particle, the two blue particles here in the middle. Look at what they're doing. They're not moving left to right. The sea does not move onto the beach. It moves up and down. So actually what we've got here is the energy moves that way. However, the movement of the wave is this way, and we'll come on to that in a minute. So a wave carries energy, and all waves carry energy. A wave is movement of energy. Now, the stuff doesn't move itself, but the energy does. And that's an important probably your first important point to note. So following on from that, we define waves as either being transverse or longitudinal. And all that means is that the wave's energy will always go this way. So there's your energy. The movement of the wave, it could either, like the one we just saw in that first diagram, first model, it could either go up or down. It goes across the wave, just like we've just looked at with water waves, etc. in the sea. And those are transverse waves. Or the movement of particles could vibrate backwards and forwards. And that way, because it's not going across or it's not traversing transverse, because it's going along the wave, it's called a longitudinal wave. So here, typical water wave, this is how light moves. So light moves by the energy goes this way, but actually the movement of the particles is from side to side, and hence waves are usually drawn like this. So we've got the displacement of the wave being up and down, or at 90 degrees to the energy direction, and you've got the direction there. Light, ultraviolet, microwaves, radio waves, gamma radiation, all electromagnetic waves that move in this way, and of course water waves. Whereas longitudinal waves are the ones where it goes along the wave. And the best example of this, where you've got these vibrations, these compressions, where it's all pushed together, and then gaps in between. So if you look at that at any point, or if you pause it for a second, you'll see that at some points they're compressed together, the particles, and at other points they're not compressed together, they are further apart. That's called rarefaction. So you've got a couple of important points on there. The displacement is along the direction of the wave, so they're both going along. That's a longitudinal one. Sound travels like this. And then you've got those compressions where the particles are pushed together, and rarefactions, areas of low pressure. So a minute ago I started doing this for the first time, and if you were in class you'd spend loads of time drawing wiggly waves. That's different to this, which is different to this. So those diagrams are all different. Some are different heights, some are different numbers of waves squeezed together. So what we have is we have common terms to describe a wave. So the first thing is the amplitude. The amplitude of a wave is the height of it. And obviously from an amplifier and with sound waves it's easy, but actually you can measure the amplitude of light waves, microwaves. So the amplitude gives you an idea of the amount of energy the wave's carrying. So you measure from the center line to the top of a wave diagram. The wavelength is exactly what it said on the tin, and this symbol is lambda. That's the symbol for wavelength. Here, the length of a wave is from the top of this peak to the top of this peak, or It's from the bottom of this peak to the bottom. It's one whole wave. It's not just one hump. This here, if I measure from there to there, it's identical to that. It's the wavelength, the length of one wave. Oh, there you go. Just like I've drawn on the top diagram. And the frequency is how many waves there are per second. So for example, we can hear sounds from about 50 hertz, that's 50 waves a second, up to a maximum of 20,000 hertz, the most screeching high-pitched noise you've ever heard. And because teenagers can hear waves better than adults, actually that's why those mosquito things outside some shops work, where they actually have they actually have high frequency waves to deter young people from hanging around. Right, wave equation. The speed of a wave is the frequency times the wavelength. And obviously when you put that in a triangle, there you've got your wave speed, v. There you have f for frequency, and there you have lambda for wavelength. Wavelength, and this is the one where you have to make sure you got your units right, in meters. Frequency in the number of waves per second, which is hertz. And wave speed in meters per second, drawn like this, or sometimes by some of you drawn like this. Either one is absolutely fine, meters per second or meters seconds to the -1. So trying that out, if we just do the first one, easy. How fast is it moving? So we want the wave speed. So it's already in hertz, it's already in meters. Wave speed was frequency times wavelength. 2 times 0.3 is 0.6 meters per second. Now what I suggest you do is pause, because I'll just show you the answers for the next three, and you can see whether you can use that or whether that's something you need to go back to My GCSE Science and continue with. Okay, there's your answers. Hopefully you've got those, or if you didn't do them and you just pressed play anyway, well, you can practice them or go back to this whenever you want. So in terms of those words, amplitude, frequency, etc., typical question, what type of wave is this? What type of wave is it? It's going from side to side, and therefore it's a transverse wave. What's the wave's amplitude? Well, what you do is you'd measure. So you might measure, for example, here, the height of the wave. So you'd get 2.2. What's the time period? So how long is each wave? And then the frequency, how many waves per second? Well, there's one wave here in 4 seconds. So the frequency is 0.25, because actually you're only getting a quarter of a wave per second. Okay, in terms of measuring the speed of waves, there's 2 experiments that we would have done in class, and one is measuring the speed of sound in air, and one is measuring the speed of water, of ripples in water. So in terms of this, what you do with the water one is we would use something that we have called a ripple tank, and it's a rectangular transparent tray of water, and it's full of water, and at the one end there's a bar lightly touching the surface of the water, and it's attached to a motor, and it just slightly moves up and down. And then what it does is it causes ripples on the water, and then you've got a light shining from above, and the light shines a shadow onto a piece of plain white paper, and you can see the waves. Now you can take a photo of that, or you can mark on there with a pencil what they are, and what you can get from that is you can get the wavelength. Then you can count, so we can get the wavelength, lambda, and then we can work out the frequency. So what you can do is you can count how many waves are there in 10 seconds and then divide by 10. And once we've got these two, you can times them together to get the wave speed. So actually it's quite easy to work out the speed of waves in water. And then you can work out the speed of waves in water when the depth of the water is different. And does it make waves faster or slower? You can work out the waves in different liquids if you want. Then the speed of sound in air. It's very easy. Somebody is here, and that somebody lets off a firework, a starting pistol, they have something loud and noise. Now the person here, 500 meters away, 200 meters away, whatever, you can work out then they see something. It might be somebody's clapped their hands together really loudly, like a big clap. And then you can see them clap their hands. How long does it take you? The stopwatch is started. How long does it take you until that sound comes to you? And we all know this because the traditional way of seeing how close a thunderstorm is you watch the flash of lightning. Light travels incredibly fast, and over those distances it's almost instantaneous. Whereas actually when you hear the lightning, or sorry, you see the lightning, boom, and then you hear the thunder, people count and they go 1,000, 2,000, 3,000. Now actually some people go, oh, the thunder came 3 seconds later than the lightning, that means it's 3 miles away. No, it doesn't. It means it's 3 lots of 700 meters away, the speed of sound. So in terms of wave fronts, go back to the ripple tank idea. Here you can see wave fronts marked there with the dotted lines, and wave fronts are used to represent the waves moving. So if you remember, originally these water waves are moving like this. They're transverse waves, the energy's going this way, but we can use wavefront diagrams to show what's happening. So this red line here is showing a beam of light. Oh, change colour pen, make it more obvious. There you go. This red line is showing a beam of light. Now it's a purple line. And then it's bouncing off this surface, it's reflecting. So these wave fronts, this bit here has hit. So here's a wave front, and this bit's already turned because it's bounced off this surface. So what could happen when a wave hits here? Well, there's a number of things that could happen, and there's specific terms for it. Now the waves could bounce off or reflect, or they could not go through, they could be absorbed by the material. So if you imagine shining light at a piece of wood, it won't go through, but it won't bounce off. It's absorbed by the wood, although there is a reflection of a colour. Or if it was glass, for example, the wave would go through. Now, if you move to a more dense material, this part of the wave is still in air, but this part of the wave has hit, so it changes direction. This part of the wave is still in air, but that part of the wave has hit a more dense material. It slows down. And actually what we get is, and then it starts to speed back up again. Because waves are affected by the density of the material they go in. And that's why if you stand in the bath, it looks odd when you look at your feet. They look closer to you because the light is bending, it's refracting as it moves from one material to another. So light could be reflected when it hits a surface, like that, or it could be transmitted or refracted through the material, like that, or it could be absorbed by the material and it doesn't get to go through. So hopefully that makes sense. In terms of reflection, the diagrams for this, you draw a dotted line and it's called a normal. Oh, normal. And then you beam your light at it. Now, how do we know which line there is a light wave? The way you know what a light wave is, light rays are drawn with a pencil and ruler and they have arrows on them. Anything with an arrow would be a ray of light. And because we're looking at reflection, the ray that hits is called the incident ray, and this is the angle it's hitting at. You always measure angles from the normal. It's hitting here at this angle, x. And what happens then is, in reflection, x is exactly equal to x. And that's what you'd get in a flat plane mirror. You get an incident ray and then a reflected ray. Angle of incidence, angle of reflection. They're both exactly the same. X is x. So, sound waves. These were the ones that were longitudinal. So the energy was going along and the wave was vibrating backwards and forwards. Now, if you're listening to this video, then the speakers on your computer, your phone, whatever, are causing a small vibration in the air with a membrane. And that vibration makes air particles vibrate, those compressions and rarefactions. That then makes your eardrum vibrate. And if you've ever had a perforated eardrum or an ear infection, you'll know how it affects your hearing, or even having water in your ears, how it affects your hearing. So, musical instruments, the strings make air vibrate. The air molecules are doing that compression and rarefaction. The vibrations pass through, they lose some energy as time, so the further you get away from a sound, the quieter it is, the amplitude is less, and it gets to your ear. And the eardrum starts to vibrate. So inside our ear, there's two main parts that absolutely help with this. There's your eardrum here, which is a membrane, which you're always careful with, and even if you stick a cotton bud or something in there, that's the bit that could get damaged with an infection. And then inside there you've got three small bones. 1, 2, 3. And those three small bones and their alignment, they actually amplify the sound, so that by the time it gets to here, by the time it gets to the part here which actually picks up the nerve endings that pick up the sound, it makes it louder, so our hearing's better. And actually some people have had ear damage with the bones being shattered by loud noises, or permanent damage to your ears from having iPods in your ear the whole time with loud noises, and actually damaging that eardrum and damaging those bones over time. So vibrations picked up in a microphone, it's exactly the same. In a microphone we talk, vibrations in the air. A microphone is made of a membrane, and the membrane moves, and then that generates a small amount of electricity. And then our hearing, 20 Hertz to 20,000. Mine is actually 20 Hertz to about 16,000. Yours is better than mine because you're a lot younger, because I'm only 21. Okay, the next use of waves is echo sounding. So because sound waves bounce off surfaces, that's how destroyers used to find submarines. And there used to be some ships that were submarine hunters, especially back during the war, etc. And now for rescue vessels, or even for treasure hunters looking for wrecks. And they bounce sound waves to the bottom, and they bounce off. So you can map the shape of the sea floor, or find a submarine, or find mines. What we use for that is ultrasound, and ultrasound, probably you've most heard of it, is when you're actually looking at pictures of babies, and most people expecting a baby have been for an ultrasound, and all that's happening is you're transmitting sound waves, and then you get echoes. Now you can't hear the sound because it's above 20,000 Hertz, so when you're looking at sound waves of 100,000 Hertz, you can't hear it when you're having an ultrasound because your ears aren't sensitive enough. The waves are going in here, and there's a reflection every time it hits a surface. Some has gone through, some reflected, some reflected, some reflected. So the better ultrasound gets, the better scan it can give us, so it can show us if there's different things. So ultrasonic waves are partly reflected at the boundary as they pass from one material to another. The time taken for the reflections can be used to measure the thickness of the reflecting surface, and the information is used to build up a picture. So all you get back into your computer is a load of reflections. Your computer then turns that into a really fuzzy image of an alien when you're looking at the baby in the womb. And then on the same sort of idea as looking inside the womb, how do we know the structure of the Earth? So you've all been taught before that we've got a crust, we've got a mantle, we've got an outer core, and we've got an inner core. And then you're taught things like the inner core is solid, and the outer core is liquid, and this is a semi-liquid. How do we know that? Nobody's ever been there, we'll never mine there, it's full of lava, you can't drill down there and take anything down there. We know it because of waves, sound waves. Now imagine doing an ultrasound experiment on the Earth and you could see inside the layers. Well, we can't do that. But what we can do is, I'll just go through those bits. What we can do is actually sound waves are vibrations, and there are vibrations in the Earth called earthquakes. seismic waves. And when they change direction because of the density, let's go on a bit. So remember, transverse waves are that way and longitudinal waves are this way. In earthquakes, we've identified a few different waves. The P waves are longitudinal. They're the ones that cause the ground to move up and down. They're the ones that knock buildings down. They're the ones in films that you see people falling about and things falling off shelves. They can go through solids and liquids, and they can do that because solids and liquids are made of particles, therefore longitudinal waves can pass through them. They're the ones that make your house shake. However, S waves, they're transverse. They cause the ground not to move up and down, it shakes backwards and forwards. They can't go through liquids. So what does that mean? So when we look at a diagram of the Earth, there's an earthquake just gone off, or a great big explosion here at the top. There's some waves heading out from that. Those S waves will only travel through a solid. And what we've found is, by measuring here, because we've got seismographs, machines to measure seismic waves all around the Earth now, what we found over time is, actually, you would pick up S waves here, you wouldn't pick them up here. And that gives us an idea that this bit here is a liquid, because the S wave can't get through it. It leaves a shadow here and here. Now, these ones, the P waves that can go through solids and liquids, have a look at those. They're refracted when they change from one material into another, and they're refracted again, but actually, because of the amount they're refracted at different stages of our seismographs measuring this, that's what leads us to believe that the centre is a solid. Also, the fact the Earth has a magnetic field. Therefore, we think the centre is mostly made of iron, a magnetic metal. So, from this, what do we know? We know that the inside of the core is a solid, the outside of the core is a liquid, and the crust on the Earth is thin. Just put this up quickly. So those are how waves can be used in everyday observable uses. And then that last little bit, it depends upon our knowledge of different waves, their speed, their absorption and their reflection. But it's taking simple things like how does sound, how does light, how do microwaves travel, and putting it into how can we use this, and actually what can we draw from that sort of evidence.